Hello everyone, my name is Takaaki Saeki from the University of Tokyo. In this video, I'd like to talk about our research for computationally efficient and high-quality voice conversion. Here is the outline of this talk. Voice conversion requires high quality and computational efficiency for practical applications, such as for mobile devices with low-power CPU. In this research, we are focusing on direct waveform modification based on spectral differentials. The conventional method using minima phase filter is of high quality, but requires heavy computational cost in filtering. In addition, when it is applied to full band case, the converted speech quality degrades due to the large fluctuations in the wider band components. One of our proposed methods is a lift training method with filter truncation. Furthermore, we also introduce subband processing for high-quality full-band voice conversion. Experimental results show that our lift training method for narrowband VC can reduce computational cost while maintaining speech quality. And our subband processing method improves the quality of full-band speech. Let me explain the conventional spectral differential VC or DIF-VC. DIF-VC is a method to construct a filter that gives the differential spectral envelope of source speech and triggered speech and apply it to the source speech waveform. As shown in this slide, acoustic model estimates the real capstrum of the differential filter, and the time domain filter is constructed from the real capstrum. This method has an advantage of avoiding quality degradation due to vocoder. The DIF-VC originally used the Mellog spectrum approximation filter, or MLSA filter, to filter source speech. But Suda et al. Found that using a minimum phase filter achieved higher converted speech quality than using the MLSA filter. Next, I'd like to explain the training and conversion processes of conventional DIF-VC with minimum phase filter. In the training process, deep neural network, or DNN, is trained to convert a real capstrum of source speech into a real capstrum of differential filter. First, complex frequency spectrum, FX, is obtained by applying the short-time Fourier transform to the source speech, and the real capstrum of source speech, CX, is extracted from FX. Then the DNN estimates a real capstrum of differential filter, CD, from CX. A real capstrum of converted speech, C hat Y, is given as CX plus CD. And the loss function L is calculated as mean squared error of C hat Y and CY, where CY is a real capstrum of target speech. Then the DNN is trained to minimize the loss function capital L. In the conversion process, CD is estimated with the trained DNN. After the high-order components of the capstrum are padded with zeros, CD is multiplied by a time-independent lifter U-min for a minima phase filter. The complex frequency spectrum of differential filter, capital FD, can be obtained by taking the Hilbert transform of the lifted capstrum. Then the differential filter in the time domain FD is obtained by applying the inverse discrete Fourier transform, or IDFT, to capital FD. Then we can obtain the converted speech by applying the differential filter FD. This filtering operation requires heavy computation, so we can efficiently reduce the computational cost by truncating FD with a fixed step length L as shown in this slide. However, such a filter truncation degrades the converted speech quality. Here, let me propose our methods, lift training, and subband processing. Here is the overview of our proposed methods. One of our methods is lift training with filter truncation for improving the computational efficiency. The other method is subband processing during conversion for improving the full-band converted speech quality. Please note that in this work, we apply these two proposed methods independently to the conventional method. First, let me explain our lift training method with filter truncation. As explained in the previous slide, filter truncation can efficiently reduce the computational cost in filtering, but it degrades the converted speech quality. Our lifter training method integrates the truncation process into training and trains not only DNN but also lifter for the Hilbert transform to compensate for the changing filter shape due to truncation. So let me explain training process of our lifter training method. As well as the conventional method, the DNN estimates CD from CX. Then CD is multiplied by the trainable lifter U, and the complex frequency spectrum capital FD is obtained from the Hilbert transform of CD. Unlike the conventional method, the truncation process is integrated into training as shown in this slide. The differential filter in the time domain FD is obtained by applying the IDFT to capital FD. Then FD is truncated to FL by applying a window function. By using the DFT again, a complex spectrum of the L-top truncated filter, capital FL, can be obtained. A complex spectrum of converted speech, capital F hat Y, is obtained by multiplying capital Fx by capital FL. And the real spectrum of the converted speech, C hat Y, is extracted from F hat Y. Then the DNN and the lifter are jointly trained to minimize the loss function capital L, which is defined as the mean squared error of C hat Y and Cy. In the conversion process, the train DNN and train lifter U estimates capital FD. Then FD is obtained by applying the IDFT to capital FD, and FL is obtained by truncating with L. We can obtain the converted speech waveform by applying FL to the source speech waveform. Next, let me explain our proposed subband processing method for full band BC. When the conventional method is extended to full band BC, the converted speech quality does not improve much due to the large fluctuations in the wider band components. Our subband processing method enhances the converted speech quality by converting each frequency band separately. In our subband processing method, the differential filter is only applied to the low frequency band, and high frequency band is not filtered. We implemented this subband processing by making the high frequency components of capital FD to 1.0, as shown in this slide. This method passes through the high frequency band of source speech and improves the converted speech quality. Here, let me show the results of experimental evaluations. Here is the experimental setup. We built two intergender VC for female to female or F to F and male to male or M to M conversion. The source and target speakers in F to F conversion was stored in the JSUT corpus and voice actress corpus, respectively. Those in M to M conversion were stored in the JVS corpus. We used narrowband 16 kHz speech and full-band 48 kHz speech for the evaluation. The DFT length was 512 samples in the narrowband case and 2048 samples in the full-band case. The DNN architecture of the acoustic model was multi-layer perceptron consisting of two hidden layers. Here is the overview of the experimental evaluations. In this work, we evaluated two proposed methods independently. First, we applied the proposed lift training method to narrowband VC. In the objective evaluation, we calculated the root mean squared error, or RMSE, by changing the truncated temp length L. As subjective evaluations, we conducted a series of preference A/B tests on speech quality and X/A/B tests on speaker similarity. 30 listeners participated in each of the evaluations, and each listener evaluated 10 speech samples. Furthermore, we applied the proposed subband processing to full band VC. In this case also, we evaluated the speaker similarity and speech quality in the same way. Here is the result of objective evaluation on proposed lift training method. The graph shows a plot of the RMSEs in male-to-male and female-to-female BC using narrowband speech. The proposed lift training method achieved smaller error conversion than the conventional method for all L. These results indicate that the proposed lift training method can reduce the effect of filter truncation. Here is the result of subjective evaluations on lift training method. This table shows the results about speaker similarity. Compared to the truncated conventional method, we can see that the proposed lift training method significantly outperformed the conventional one in terms of speaker similarity. Furthermore, compared to the non-truncated conventional method, the proposed lift training method had the same or higher quality. These results indicate that the proposed lift training method can reduce the tap length to 1/16 without degrading speaker similarity, whereas the truncated conventional method significantly degrades speaker similarity. This table shows the results about speech quality. In this case, the same tendency can be seen as the results about speaker similarity. To sum up, those results indicate that our lift training method can reduce the tap length to 1/16 without degrading speaker similarity and speech quality in the narrowband case. Here is the results of subjective evaluations on subband processing in the full-band case. These tables show that the proposed subband processing method achieved a higher score than the conventional method, excluding the speaker similarity of the M2M BC. These results indicate that proposed subband processing method improves converted speech quality. Here are some demonstrations of F2F conversion. First, I'd like to play the source speech and target speech.
カーミラ星と呼ばれている惑星から宇宙船に乗って地球に侵入した宇宙人。
カーミラ星と呼ばれている惑星から宇宙船に乗って地球に侵入した宇宙人。
The first demonstrations are comparisons between the conventional method and lift training method in the narrowband case. Let me play the converted speech using non-truncated conventional method, truncated conventional method, and truncated lift training method.
カーミラ星と呼ばれている惑星から宇宙船に乗って地球に侵入した宇宙人。カーミラ星と呼ばれている惑星から宇宙船に乗って地球に侵入した宇宙人。カーミラ星と呼ばれている惑星から宇宙船に乗って地球に侵入した宇宙人。
We can see that lift training method is of significantly higher quality compared with truncated conventional method. The next demonstrations are comparisons between the conventional method and subband processing method in the full band case. I'd like to play the converted speech using conventional method and subband processing method.
カーミラ星と呼ばれている惑星から宇宙船に乗って地球に侵入した宇宙人。カーミラ星と呼ばれている惑星から宇宙船に乗って地球に侵入した宇宙人。
We can see that the converted speech with subband processing is clearer than the conventional method. Here is a summary of this talk. VC needs high quality and computational efficiency for practical applications. Conventional deep VC is of high quality, but requires heavy computation. In addition, conventional deep VC degrades the quality when applied to full band case. In this work, we propose two methods, lift training with filter truncation and subband processing for full band VC. Experimental results show that proposed lift training method can reduce the tap length of the differential filter to 1/16 without degrading converted speech quality. Furthermore, proposed subband processing can improve the converted speech quality. Thank you for your attention. If you have any questions, please feel free to ask us.